ברה וקט. מה זה ברה וקט? זה ברה וזה קט. כשאנחנו כותבים ברה קט, בדרך כלל עושים ככה. כלומר, אם נגיד נעשה ברה, פסאי, קט, פסאי טאג, אז מה? קט זה רק עם קו אחד באמצע, ולא שתיים.
אני לא בטוח אם הוא...
אוקיי. בוא start. I answered her question. זה מעולה שמעת לי. Brown cat.
Yeah.
So we're just doing a little bit of a repeat. What is brown cat? This is bra, and this is cat. Together, we write it like this. Brown cat is like a state in the Hilbert space. Which means it's a state in some space. Some space it spans all the options. We just say it's not rigorously at all. And if we do bra and cat like this, we can write it as an integral also, as psi dagger, psi tag, the something. What is this? This something what? The what? So if I have psi of x, psi tag of x, it will be psi dagger of x, psi tag of x, dx. What we do here is, in a sense, we measure something a lot of the times. For example, if we want to measure the momentum, we can write the momentum of this wave function. We can have psi of x, p operator. We can do operator, we can do a hat. And psi of x, for example, what is the momentum? And then we will have an integral psi dagger of x, p operator which operates on psi of x dx.
Okay. And what if you do only one side?
Okay.
Or the bra or the cat?
Or the bra, okay, great question. Does this remove stuff? Yes. If we do, for example, if I operate p over some function, sometimes if this operator is in the same space of those eigenfunctions, we will talk about it shortly, we will have this, let's say this is p operator, we can have p and I can write in value psi, which means we get the eigenvalues of this function. But it doesn't happen for any psi. It happens only when psi is an eigenvector of this operator.
Can I ask you, what is the intuition behind this definition?
What is the intuition behind this definition?
Because when you say the bra and cats are together, you want to calculate something because you do like maybe projection or something like that, right? But if I use the operator on psi and then I do it in the bra and cat, what is the intuition that it would do?
What's the difference between this version and this version?
No, I mean, okay, I want to know, say, the expected value, right? The average of the momentum.
Yes.
And then I use just this, I don't know.
Maybe I didn't understand you correctly, but I'm gonna give one example of what happens here.
Okay.
If I'm doing an experiment, I have a particle. Okay, starts in some, let's say this is the origin, this is x, this is y, and we are looking for average value of x.
Okay.
Okay? What I'm gonna get, for example, I'm gonna have a first trajectory of the particle. He starts here, he goes, comes here, stops, and I measure it. I measure it over here, so I get x. I can say x measure 1 will be, and let's say I measure only x, I don't care about y, will be, let's say 3. And this is 1, 2, 3. Then I'm starting the experiment again. The particle moves, come here, let's say this is -1. So x measurement 2 will be -1. If I repeat this experiment 1,000,000 times, 10 to the 8 times, what I'm gonna get is, so I can say that the average, I can write it like this, I can write it like this. It doesn't matter too much for this course how I write it. I can say it's like 1 over n, capital N will be the number of experiments. Sum over I equals 1 to n, x m I, the ith measurement of x, divided by n. So this means I'm just taking an average in the experiment. But here I have an average which is something analytical. And we expect those two averages to converge, to be the same number, when we have enough experiments. When n goes, capital N goes to infinity. If I look at the example of this particle, which is making some movement, jumps, moves, I don't know, let's say it's quantum, it can be also classical, it doesn't matter. Let's see it's symmetric, the system is symmetric. So x average will be a lot of the time 0, because it doesn't have any preference to go to the right or to the left. So on specific experiments, it's gonna go to the right, or it's gonna go to the left, or to the left and then come back. But on average, it's gonna be 0.
Okay.
If you look, for example, a lot of the times when you look at such models or such processes, we do want to get something. If you say x average is 0, we don't have almost anything. So we can go, for example, to higher orders. We go to x squared, or the variance. And then we get, I don't know, something like 2, some constant t. I don't know what it is. Sometimes it's going to depend on time. It's okay if it's going to depend on time. It's not going to depend on the x because it took the average over x.
Okay.
This is some intuition. Questions so far?
So why do you need to use the operator on psi and then multiply? I mean, what's the intuition behind defining it like that?
So, why we use the operator on psi and then multiply by psi? So, let's break it down. First, I'm gonna erase this one. Let's think what we have here. Here we had some operator. We operated on psi, and because we are lucky and we choose psi correctly, we got the eigenvalue, p-value times psi. If you look on psi, p operator psi, this is not equal to p operator psi psi, right? Because this is an operator, I need to operate it. However, it does equal to a p-value psi psi. Why? Because here, if I operate, I can say I add an operation. I operate bra psi on the left. Here it's just a value, just a constant. I can move it outside the bracket, but when it's an operator, I cannot. And it depends on what is exactly psi, if I can or cannot do it. So this is illegal, only when this applies. This equivalence applies. Okay. Questions. Today it's going to be a tutorial that we already did, kind of, in some manners. I don't know how it was. Richard asked me to do it today. So it's a great opportunity to ask many questions. Also, if at any point I say something in English which is not 100% clear, you can ask me also in Hebrew, and I repeat it also in Hebrew and in English. Think the number? Okay. Yes.
Can you please repeat about the
מוחלט?
מוחלט, הפיגוע, אמרתי שזה חשוב, במידה, כאילו שאם אני רוצה חילוק יותר,
רוצה שנדבר על זה קצת, בדידות. אוקיי, we can keep going.
כן, אבל הסדר השני. אתה מבין? כאילו, לא רק התוחלת, התוחלת של הערך בריבוע.
What we talk about the, let's say, the second moment, or the variance.
כן, yes.
So, previously, I spoke about, let's say we have a particle which doing some diffusion or movement on the x-axis. For example, this is the starting point, so sometimes it goes to the right, sometimes it goes to the left and then to the right, and then back to the left, and so on. And just to give some arbitrary examples. So when this system is symmetric, we will have that the average value of x over many experiments will be 0. Because it has the same probability to go to the right or to the left. It could, the same will be applied to waves which propagate to the right and to the left simultaneously. But the second moment, so when we have a system, we want to describe a system, a lot of times we say, okay, let's look at the moments. It describes very well the characteristics of this process. So when the first moment is 0, we almost don't know anything. So we need to go to the second moment. And if the second moment will be, it goes to 0, for example, what we have is a delta function. If it goes to infinity, so we have some uniform or something. But it gives us the width of the wave packet.
The what?
The width of the wave packet. Okay. More questions?
Okay, just making sure I
Yes.
understood. You say this works because I can say psi as a superposition of the eigenvectors of the operator P, then
Psi
of the
okay.
operator P, and then I use this equation, right? The eigenvalues of it, and then I get actually the from probability. Right?
I think the way to say it is what we have here is an operator. So if we think about it as in linear algebra terms, you have some operator which works on some eigenvector. So if we have an operator, this is operator, this is vector, when it will be equal to some value times the same vector, only when this operator is diagonalized.
Is what?
Is a diagonal, has only items on the diagonal. And then we can just say, okay, it's some constant. In some minutes, it's some constant.
So, but psi is not necessarily an eigenvector, right? So I use okay, I think I understand.
It just, an eigenvector will be something that if you have an operator applied on it, you will get a value times the vector.
Yeah, I know. I'm just saying that. So the intuition behind this definition is because I can write psi as a superposition of the eigenvectors of the momentum.
Yeah, but even if you cannot, you might find here some meaning. Because what I have here is I have some eigenvalues. But even if I don't have eigenvalues, I still have an integral.
Yeah, okay.
But
But
it's
it
just
creates my intuition, okay.
I still have an integral and I can still find some meaning maybe.
Okay. So, okay, but the intuition from your, okay.
So it's great, I'm gonna repeat this tutorial.
Yes.
And let me know when I should go faster or slower. Okay, all good. I can erase everything, right?
This is תרגול 4
This is,
on the model.
I put it in the Moodle like 5 minutes ago.
Okay.
It's the last one. I think it's TA4, maybe TA5. This is recorded.
כן. בסדר.
Okay. Moreover, a note regarding the homework. It is very important for you to do the homework. If you're gonna submit late, as long as it's not like a month late or 2 months late, I don't mind. But you should do it to the best of your abilities. Work on it, try to understand it. If you have questions, you can ask me, you can ask Richard, you can ask your friends, ChatGPT. ChatGPT is part of your friends now, okay? And yeah, work on it. It's important so you'll be able to understand and be ready also for quantum mechanics. Okay, perfect. So let's talk about the momentum operator. We're going to talk about operators, hermiticity, expectation values, and the uncertainty principle today. feel free to ask me as many questions as you like, and I will start doing it a little bit faster because I think it's your second time. Okay, so P operator times some psi of x. I can add here a hat, or I can add it over, it doesn't matter. Equals to minus I h bar dou to the x psi of x. Great. If this psi of x is an eigenfunction of this P operator, and only if it's an eigenfunction of this operator, we get that P operator psi of x equals P value psi of x. This is what I said at the beginning. Okay, so when we have this expression, when you know exactly what is P val, we're making like a little bit of a toy model, but it's good for intuition. We can get what is this, what is the eigenfunction which satisfies this operator. For example, I can say, okay, so this is equals to minus I h bar dou x psi. When I can write here, like, I can cheat a little bit, but there are no mathematicians, d psi to the x. Okay? So, and let's say I'm gonna write only p when it's a value. So what we get here, we get that d psi over psi equals, and I can, let's do it in two steps. P times d psi over psi. Sorry. Let's do it p dx. 1 second, minus I h bar d psi over psi. Yes.
What are we doing? Solving the...
We're finding what can be psi of x, which is an eigenvector. What kind of eigenvector do we might get for psi of x? How we do it? We start from here. We say, okay, let's say it's an eigenvector, meaning we get some p, a result, a value, eigenvalue. Then we use this relation and this box to come to this expression and find psi using some ordinary differential equations. So this differential equation I can write as, let's do d psi over psi integral equals ip over h bar dx integral. Meaning log of psi equals ip over h bar x psi, and I can add here some constant plus a. So psi will be equal to some second constant, a tilde, e to the ip over h bar x. And this is psi of x. Which means we get that an option for the eigenvectors is the free particle. If we consider a little bit more carefully, we know that P is over or divided by, let's say, P equals h bar k. So psi of x equals some constant d I k x. Interesting. This really reminds us of the Fourier transform, which is very interesting, as we know that the Fourier transform can span all the bases, meaning it's a valid solution for any kind of wave function. It can describe everything in some sense, when we sum over all k, of course.
Can you repeat this?
So, in the previous tutorial, we had some psi of k of x, or psi n of x, which is something which determined by also the quantum number n, or the quantized number, which depends on the initial conditions or the boundary conditions. And then what we said, okay, psi of x equals some a summation over all n from 0 to infinity psi n of x, all the specific modes of n. Here we see we get something similar. We get some k, which is free for us to determine. It could be anything. Meaning, if we're gonna sum, I can write this as psi k of x, and psi of x can be defined as some integral over all possible values of the k, psi k of x, and then I can add some g of k. G of k will be like the weight, the weight, or it's going to be the same as like c of k, the weight of each mode k. The probability, in some sense, it will be related to the probability of having psi k or x being in a specific mode k. Questions? Okay, I'm trying to go a little bit hard with the intuition, so feel free to ask anything. Okay. We'll make another step looking at what this a tilde is. Okay, so let's circle this expression and find what is a tilde. How can I do it? So when I have a constant here,
Normalization.
by normalization, great. So I can find a tilde by normalization. Meaning I can do Brine cat and say psi k of x, psi k, and I can say let's do k tag of x. And I know that by normalization this must be equal to delta k minus k tag. Or to be more precisely, k comma k tag if we're doing this other delta. Because I want it to be 0 when the k and k tag are different, and 1 when they are the same. Okay? So by definition, var psi cat will be equal to an integral. Yes?
No, I'm saying it's a tilde squared times.
Yes, exactly. So I can do a tilde e to the minus ikx, a tilde e to the ik tag x dx. You understand why there is a minus here? Yes? Yes, for sure. Why there is a minus?
The complex.
Yeah, the complex conjugate or the diagonal. Exactly. But this must be equal to, so this is equal to a tilde square integral dx over e to the minus ix k minus k tag. And let's say how to do the tutorial. And what we want to do now so one way to do it is to just say when k equals k tag, we have here a 1. But let's see how to play. 1 second.
You
Okay.
represented the Dirac.
I can just write the representation. I thought I will have to prove it, but I can just represent the Dirac delta. You're right. So okay, the Dirac delta of k minus k tag is defined to be an integral of the x over 2 pi e to the I k minus k tag x. Now this is the definition of the Dirac delta. So by this definition I can say that this part, this expression equals to, so I can just say that the a tilde squared must be equal to 1 over 2 pi. Because this is the only way that we get the delta that we expect. Okay? So a tilde is equal 1 over square root of 2 pi, and we ignore the global phase. We talked about last time, because we don't care about it now. Okay, so now when I plot it into here, I get the following expression. We get e to the I kx, and we can write it dk over square root of 2 pi g of k. Very interesting. What does it mean? It means we get the Fourier transform of the inverse Fourier transform of the function g of k. What is g of k?
What did you say?
I just plotted here psi k of x. And I have this psi of x equals dk over square root of 2 pi e to the I kx g of k.
So we use Fourier transform.
It's the Fourier transform, g of k. I mean, this is g of k is the Fourier conjugated of psi of x.
Where did the G of K come from?
I put it manually. I said that by definition, manually it means באופן ידני.
Okay.
המצאתי את זה.
Okay.
I invented this expression. Meaning I said that if we know that a specific model function psi n equals, let's psi n of x equals, for example, x to the n. I don't know, just giving an example. So I can span, and I know that these span the basis. I can say that any function, let's say f of x, will be a sum or an integral from n goes from 0 to infinity, if n is an integer, of psi n of x, and then I can write here cn, which is the weight.
Okay, so CM מקביל to G.
Yes, exactly. I can also write here an integral, and sometimes when we have a summation, we write cn, and when we have an integral, it becomes some,
Function.
let's say this is the n, g of n, gn. It doesn't have to be, yeah, g equal g of n to make it look similar, and then psi n of x. Cn and gn are both functions. This is just a discrete function.
Thank you.
You're welcome. So we know this spans the basis, and because we found out this is the inverse Fourier transform, we can say, okay, those are Fourier conjugates. Okay. Questions?
Yeah. You said ignoring the global phase, right? Why is it called global phase?
Because it's the first one. The first one is that I can say it's a global phase. We can ignore this phase. There is some e to the I theta.
No, I'm just saying, why do you call it
I could call it the global phase because it's the first one I saw. So the first one, so I can say that one phase in the system, in any system, is a global phase. Because we have one global, because when we start the experiment, we don't know to what t equals what we start the experiment.
Oh, so you say everything can be...
We can just say t equals 0.
Relative to that.
Relative to one phase,
Okay.
yes. So we can determine one.
Okay.
So we got that the Fourier transform is the eigenvector of the momentum?
Yes, exactly. What we got? We said, okay, what we got is that we try to find some eigenfunction that satisfies the momentum operator. Okay? This eigenfunction was a free particle.
Because there's no potential.
Because there is no potential, something
That's what we say.
very easy. It's not like if we had a potential, for example, if we have some h psi, sometimes what we have as eigen vector is some e times psi. And here we have sometimes the potential, sometimes not, whatever. If it's a free particle, the energy would be very similar. We get still a free particle for the wave function or the eigenfunctions. Anyways, so yes, the intuition is a little bit crude, but we work on it. We try to look for some eigenfunctions which satisfy this equation. We did a little bit of differential equations and a little bit of normalization and examples, and we got that some mode could be a free particle with k. K, we call it the wave number. And we saw that because this is only a specific mode, we can have all the different kind of modes with different weights for each mode, g of k. G of k is like the weight or the density, or you can call it in a lot of terms. And I try to use a lot of words to make it more intuitive. Then we can find out what is psi of x. Why this g of k is so important? How is it different from one problem to another? This g of k is going to be determined by the initial conditions. Okay? So, okay, great. We are happy.
Yes.
Okay, so we're gonna give a little bit hint of regarding the uncertainty. So what we want to do is we want to say where is the particle? What is the probability of this particle? We got a wave function. We got something which describes a particle or something or some object. What is the probability to find it in some specific place x? So I'm gonna do something which looks a little bit stupid, but it's true.
Classic.
I'm gonna say the probability of a particle to be at some specific x, the probability density. We can say this is rho of x, this is how we denote it. This is psi of x, absolute value squared. If we look at here, we're gonna get that this rho of x will be equal to 1 over 2 pi, and that's it. Huh? 1 over 2 pi, because an absolute value gives
Okay.
e to the minus I kx, e to the I kx, which is 1 over 2 pi.
I think.
So the probability to find the particle at some specific place x is 1 over 2 pi. What does it mean?
You have same probability.
We have the same probability for anywhere. What does it mean? That we don't know where the particle is. We don't have a clue. It doesn't have any preferable place to be. Why does it make sense? It makes sense because we have a free particle. If we have a free particle, we don't know where it is. It's a free particle. It doesn't have any preferable location across the space. Yes.
Just so I know, you calculated based only on the eigenfunction of k though, right?
Right.
Shouldn't you do it on the entire integral?
Yeah, this is for a specific k. But if we don't know for a specific k
Okay,
where it is,
okay.
we don't know for any k where it is.
Okay. Okay. Thank you.
So this gives us some intuition about the uncertainty principle. Also, what we do know about this specific k, we don't have a clue. Let's add here a k. Let's say this is given k.
Oh, you know the momentum because
We know the momentum. We know the momentum exactly. So because, in some way, because we know the momentum exactly, we don't have a clue what is the location. Where is it? Cool. Very, very cool. We love quantum mechanics. Okay. Questions so far? We're having a lot of fun today. It's great. Because I did a little bit in the start, I don't want to repeat myself again. So let's look. This is a little bit overwritten. This is the most time we have. Let's talk about hermeticity. Okay, what is hermeticity? How we define it? One way to define it, when some operator is emission, when an operator is emission, we have that for some arbitrary functions, psi1 and psi2, this could be any kind of functions. Psi1 dagger, f operator, this is some operator, psi2, and let's say the x, doesn't matter, equals to an integral over f operator psi1 dagger psi2 dx. Basically, one way to see it is that f operator equals to f operator dagger. This is when an operator is emission. So, in general, Hermitian operators are important because they are what we can measure. If an operator is not Hermitian, let's say if the momentum operator was not Hermitian, we couldn't measure momentum in the lab. Because this we can measure momentum. Okay. A few important notes about Hermitian operators. The eigenvalues, if I have some f operator which works on some sign, we get some value, let's say f value, the same sign. If f operator is emission, f value is real. It's not a complex number, it's a real number. This is one point. A second important point will be that the eigenfunction, if this psi, if let's say if psi is eigenfunction of f, or of some f operator, of any kind of emission operator, we have, let's say psi n, we have orthogonality, meaning psi m would be delta n m. So emission operators are very, very good for us in some sense because we can measure them. The values we get are real. This is what we measure, the values. Because what does it mean when I measure these values? Because when I want to measure this operator, I'm writing psi. I'm gonna do it in another color. When I measure this f operator, I'm doing psi f operator psi, and I get f value psi. Because it's the same function, it would be f value, and we measured f operator. Great. And yes.
Why you could... בקיצור, למה יכלת להוציא את זה, להזיז את האופרטור שמאלה?
I didn't move the operator. I'm gonna answer in Hebrew and then in English. לא הוצאתי את האופרטור. הפעלתי את האופרטור על פסאי, כי אני יודע שאני יכול לקבל עליו את הערך עצמי, ואז את הערך עצמי הוא קבוע בתוך הבלבקת, ואז אני יכול להוציא אותו. So what I did is, I operated the operator on psi, then I got the eigenvalue times psi, and because it's just an eigenvalue, a constant, I can take it outside of the Brand cat. Then because this satisfies orthogonality, we know that this is equal 1 if it's the same sign, which it is. That's what I measured. Okay. And number 3 is complete set. What is right? With a complete set. Meaning the eigenfunctions of the Hermitian operator spans a complete set. I can describe any kind of function using those eigenfunctions. Okay. Great. Let's have a small exercise.
Yeah.
We want to show that the momentum operator is Hermitian. And I'm gonna do it just to make you more familiar with stuff like integration by parts. Let's see shortly. So we want to look, let's have this expression. Let's have this psi 1 down here. Let's have P operator, psi 2 dx. This is where we start and we try to end over here. Okay? This is equal to psi 1 dagger minus I h bar dx psi 2 dx. Now we can have integration by parts. IBP, integration by parts, because we have the integrated, unintegrated, and so on. So what we get is minus I h bar, I can take outside everything. Psi 1 dagger, psi 2, minus infinity to infinity, minus an integral, and now we change the derivation from psi 2 to psi 1. So
What is the F and G?
So F is psi 1 dagger, and G would be d dx psi 2. And d dx psi 1 dagger psi 2 dx. Okay. So from this side we see we already very close to get this description. We're very close. We're not there yet, but we're close. But here, what we have here, 0. Why?
From the limit and find them at infinity.
Right, but why? This is 0. Why is it 0? So we say the functions, the wave functions must be 0 and plus and minus infinity. But why is it so? The reason is, those wave functions, it's not just regular wave. It's not like a cosine wave or a sine wave. It's a wave of probability. Okay? And in order to have this wave function normalized, we must have that an integral from minus infinity, we must have that an integral from minus infinity to infinity of this wave function, the x must be 1. However, if at minus infinity or at infinity we have some non-zero values for psi x, this integral will diverge. It will never be able to be 1. Because if we still have terms with sum up, when we go to infinity, we can go to infinity infinitely many times. So we can have infinitely many terms which are non-vanishing. So this must, when this is applied, we know that psi, this is for any kind of function, psi of plus minus infinity must be equal 0.
I don't get it.
This is a claim.
Say God.
This picture of why psi of x must be 0 at plus and minus infinity?
Yes.
What's bothering you?
למה
Here.
מכפלה ביניהם שם?
Because if
היא אפס.
So what we are having, we have psi 1 dagger at infinity times psi 2 at infinity minus psi 1 at minus infinity times psi 2
ובהגדרה כל אחד מהם הוא
at infinity.
אפס.
Exactly.
אוקיי, תודה. And another question.
Yes. Perfect.
באינטגרציה בחלקים אנחנו עושים f כפול g, אבל בחלק השמאלי של המינוס סוף עד אינסוף, איפה g?
זה G. This is G.
אבל הוא גם כולל נגזרת בתוכו, אז מה...
לא, this is G tag. זה G tag, נכון?
אוקיי.
אז מה יהיה G?
ספר באינטגרציה, נכון, סבבה.
My bad. So she asked where is, because this, I didn't know the derivative, so I was a little bit confused. But what is the G here?
תודה.
Perfect. Okay. We are very happy. We are doing great.
Yes.
This is equal to an integral. Let's write it in x. Something about the minus doesn't. It's great. It's great. It's very, very good. So we have. No. I have minus, right? I have IH bar?
No, you must not have minus. Because you want it to be the...
Of course,
Of
yes, exactly. So I have IH bar d to the x of psi 1 dagger psi 2 to the x. This is not P operator. This is P operator star or dagger because of the minus. So what we can do, we can just take, is it dagger? I can just take the dagger out, but I didn't mean dagger, I meant star and conjugate all the way. Yes, it just means.
Does it matter?
Yes, because dagger is like conjugate and transpose, so it will switch between the two. Right, yeah, I just copy it. So this is dagger, the conjugate, and we have integral dx, P operator, psi 1, conjugate, psi 2, dx. The important part was the integration by parts, and also in the tutorial it is a lot of stuff moving here. Okay. Great. So we have a lot of operators. We have many operators. We have the momentum operator, the displacement operator, we have a kinetic energy operator. We have a lot of operators. You already had an exercise, having a lot of fun with those operators. To name a few of them would be, I'll give an example where we have, okay, so P operator, we know it's minus I h bar d to the x. E operator, the energy operator would be I h bar dot to the t, where we say that it equals also to H operator a lot of the times. T operator, T is not temperature, it's kinetic energy. Right now, we can define it as P operator squared over 2m, which is minus h bar squared over 2m dot to the x squared. And V operator would be V of x operator. This is some general intuition. We have a lot of operators. Okay, what we have left? We have representations. This is not important. photos in momentum space. Okay, we should do it. We should keep going. So I want to emphasize on the example first, and if we have time, we can get back. Look, I want to talk about the free particle wave factors. It's an important example, so I want to do it.
הייתי אצלך מילה.
רק את זה חמש, כן. כאילו חבילת גלים. So, we have some wave function. We consider the wave function, say of x equals a e to the minus alpha x. Where alpha is some constant. And also a is also some constant. So we have two constants. What we want to do, we want to find the average value of x, the second moment of x, the average momentum, and the second moment of momentum. This is what we want to do. Also, we want to compute the expected value of the kinetic energy, or the average of the kinetic energy, or the average of the kinetic energy, T. Great. So, we want to find what is, and also let's have A, because we can always find A from normalization. Can we find alpha? No. We don't know. It's like A. It could be anything basically. So A. So if we start by finding A, psi of x, graph psi of x, ket psi of x would be equal to psi dagger psi dx, and we know this must be equal to 1 for normalization. This is normalization. This is equals to a squared integral from minus infinity to infinity e to the minus 2 alpha x dx. This is equal to 2a squared integral from 0 to infinity e to the minus 2 alpha x dx. Because this is symmetric, a symmetric function, integrand, we can just change the boundaries to 0 to infinity, from minus infinity to infinity to 0 to infinity and multiply by 2. And now, because x is only positive, we can remove the absolute values of x. This is equal to absolute value of a squared. We can have here absolute value also, and here over alpha. Meaning, now I'm going to write it here, a is equal to square root of alpha. Questions? I'm gonna remove this, because this was just a short exercise. What is average value or expected value of x?
Maybe 0.
0. What? Why?
Because it's symmetric and it has the same probability to go there and there, and so
Exactly. Because psi of x equals to psi of minus x, or symmetry. You can also say this is equal to an integral a squared e to the minus 2 alpha x times x dx, or minus infinity to infinity.
that's antisymmetry.
Is antisymmetric function with symmetric boundaries. It is equal to 0. So, what is the second moment of x? So this is equal to an integral a squared x squared e to the minus alpha absolute value of x dx, minus infinity to infinity, equals to 2a squared integral from 0 to infinity x squared e to the minus 2 alpha x dx. How do we solve this integral? Integration by parts. Exactly. This is a great solution if you don't like yourself. What I'm gonna do?
I don't.
Okay. I can give you a great number later.
Or you can differentiate e to the minus 2 but according to alpha, and then you get like
Exactly.
What's the difference?
Differential like so. Okay. So what is x e to the minus alpha x? Or let's say x to some e to the alpha x. This is equal to d to the x of e to the alpha x. D to the alpha. Great. This is a great trick. If you have here x to some integer n, to be the n to the alpha n. So this is equal to wrote it here nicely.
why do you get minus 2 alpha x?
Why do I get?
If-
Right? Because I also have minus 2 alpha x.
Oh, okay, because it's staggered.
Yeah,
okay.
the stick was
Oh,
here
oh,
because I have psi times psi.
Yeah.
Psi
Okay.
times psi. Great. So, what we have here is an integral from 0 to infinity d squared over d alpha squared e to the minus 2 alpha x. The minus cancels out, but we get also 4, so we can have here 4. This is the 4 from this 2. Yeah. And because we differentiate according to alpha, and the integral boundaries don't have any alpha, and also the summation is not over alpha, I can say this is equal to a squared over 2 d squared the alpha squared integral from 0 to infinity e to the minus 2 alpha x dx. This is much better than integrating by parts. Okay, don't do it in the exam, go this way. I hate integrating by parts so much, I'm not gonna even give the example of how to do it here because it's like it's a few lines and I'm lazy. So x squared is equal to, we can insert the alpha to the a. So we have alpha over 2 d squared over d alpha squared of 1 over 2 alpha. And this is equals to 1 over 2 alpha squared. We are happy. we are very, very happy. We can have also some intuition to what it means. This is, in some sense, the uncertainty in space. Meaning, if x squared, or if because the mean value is 0, so this is the same as the variance. You can also say the variance of x, only because the mean value of x is 0, let's say. So the variance is in some sense the uncertainty, or if we have, let's say this is x, we want to look at what is the probability to find the particle at some place x. We know that the expected value would be at x equals 0. This is the 0 point. And the width of the packet, or the width of the probability of finding, will go something like the variance. Okay, so something which goes like x squared. And this is the whatever we have here. Which means it goes like 1 over alpha squared. So when alpha is very big, very, very big, we get a delta function. And we see here when alpha is very, very big, what do we get? Let's look. This is some general intuition when we consider such problems. Let's look at the large alpha limit. So we said here we're going to have some delta function. What is psi of x? Psi of x is, and I can remove, let's say we have some constant e to the minus alpha x. When alpha is very, very large, because this is x absolute value of x is always positive, this also goes to some delta of x minus 0. Because it's like it's a 0 for any finite x. This is in the, okay, let's write it again. In the limit of alpha goes to infinity, e to the minus alpha x goes to, and let's say some constant, c0 times delta of x. Because when x is 0, we're going to get some constant, we're going to get 1. So I can just write it 1. But when x is, let's say 5, e to the minus 1 million times 5 is 0. So we get something which coincides. We don't have any contradictions in our theory. We saw that the mean value is always 0, also in the large alpha limit, and we can say that the width of the package goes to 0 when alpha goes to infinity. Just we try to play with the math and the physics and try to see if we don't have any contradictions. Okay, makes sense. Questions so far? It was a little bit confusing, I'm sorry.
No, it was great.
It was good? Okay.
Yes.
Okay, great. It's right here. 1 over 2 alpha squared. Momento. We love momento. Okay, so we want to know what is the mean value of the momentum. We're gonna do a little bit of a trick.
Is 0 as well, right?
Hmm?
I think it should be
Why?
for 2 reasons. First, we saw that if the psi is real, then the average of p must be 0. I think.
If
the psi is a real function. I think Richard said that. And the second, if it wouldn't be 0.
no, again, repeat it. If psi is real,
I think
the
Richard
average
said.
momentum should be 0.
I think.
What does it mean psi is real?
Like it doesn't have any complex term, let's say. Or the other way around. Okay, maybe it was the
No,
other way
it
around.
might be true. I don't know. Let me think about it for a second.
Maybe I
If we
don't
have
remember
a real
correctly.
function, the momentum, the average momentum should be 0. It is 0 over here, so it might be true. And if we just said it, so he's right. He's smarter than me.
I think it's that's what he said, because if you try.
Let's try to understand it.
But the second reason is because you find you found that the expected value of x is 0. If the momentum wouldn't be 0, it would go away. And so you want, right? I mean, suppose the average x is 0, and the momentum is not 0, and the particle would go to infinity.
I agree.
And so it must be 0.
I think you are correct. What it says basically is, if we have some, I'm not sure it's correct. I really am not sure, so maybe I just shouldn't repeat it, though.
I'll ask him.
You can ask Richard, maybe for real valued functions, the momentum must be 0 if the displacement is 0. This is what you said, right?
No, I think in general it would be 0, but I need to ask him. Maybe I don't remember correctly.
Maybe. You can also send me an email, I can check it later if you want. Or you can send Richard an email. He's a very nice guy. Okay. But it is 0. So it is 0 here in this example, but we want to do it. We want to go a little bit of some tricky way to do it.
But you can ask whether my explanation, the other explanation, is correct in
Which
any
one?
case, right? If the average x is 0, then it cannot be that the average momentum is not 0, right? Because then the particle would go to infinity and it wouldn't be
I think what you say is correct, but I don't know.
okay.
I don't know. It sounds right, but it's the stuff ChatGPT can tell me, and I can say, do I believe him? Like, I need to check. I don't know. Like, maybe it is correct, maybe it is true, but I don't know. So I'm not gonna say it is true. Maybe. It sounds true. It's, okay. So, what we can do to find the momentum, which is 0, we already know it. What we can do, we can also use the psi, not psi of x, but psi of k. We can do it as psi of k p psi of k. And I always love to add a tilde to distinguish between psi of k and psi of x, because it's a different function. We can just say we have here an integral over psi tilde of k dagger p and psi tilde of k dk. Why am I doing it this way? Because p operator in Fourier space is just variable. So I'm a little bit going over.
But we don't have the you want to do the Fourier transform כדי לתאר את זה ב-K, ואז אחרי זה לעשות
Exactly. So, did you understand only this transition? Is it clear to anyone? Or I can do a little bit of a recap, short recap of basically, we're going to do a short recap anyway. I think it might be good. We know that in position space, X operator is basically X, and P operator is basically minus I h bar to the x. However, if we look at momentum space, or Fourier space, we get that X operator is minus I h bar minus I h bar to the p, ddp, and p operator basically p. Okay, this is just in short. I think you should all know it. I want to just note that there is a symmetry here, where they have the same wall, but not in the same space. Meaning X operator is very similar to P operator in momentum space, and vice versa. So this is why we would like to do it in Fourier space some of the time. Sometimes we can just do it in X space and take the derivative, meaning using this expression to P operator, and solve the problem. However, because of the absolute values, it might be a little bit hard to do. Great. Okay. We are doing very, very great. So happy for us.
I think the 10. The 10.
I always take a picture of the board and I never ever look at it. Okay. So where we were at. So we want to find this psi tilde of k. What is psi tilde of k? This is 1 over square root of 2 pi Fourier transform e to the minus I kx psi of x dx. And I believe you can do it.
Yes.
This is equal to square root of alpha over 2 pi 2 alpha squared plus k squared. Questions on how I did it? You can ask Wolfram. Perfect. P average is equal to, and of course I can have P is equal to h bar k for this P. So in an integral, let's have an integral of decay. This is just a value k, so I can have here h bar k. This is our P. And then we have alpha over 2 pi, 2 alpha over alpha squared plus k squared squared. From minus infinity to infinity, and this is equal to 0. Why is it equal to 0? Because it's antisymmetric in symmetric parts. Nice. Now, it is important to do it because we want to have the second moment, and it's going to be quite easier. Because what is p squared? It's going to be equal to, I can have here alpha h bar over 2 pi integral from minus infinity to infinity dk k squared. I just instead of k here I put k squared and also h bar squared. You're right to correct me. And 2 alpha over alpha squared plus k squared squared. Which is equal to h bar squared alpha squared. This is very interesting. Why? Because x squared, it goes like 1 over alpha squared, but over v squared, it goes like alpha squared. Meaning if you go to very, very large alpha, the answer, we know exactly where x is. Because what we have previously is, we said that when alpha goes to infinity, we have basically a delta function. However, the uncertainty or the variance in p, in the momentum, diverges. We don't know anything about the momentum. We know anything about the displacement, we don't know anything about the momentum. We can have the same exercise when alpha goes to 0. When alpha goes to 0, we're gonna have that the momentum, the variance in the momentum will go to 0, but the variance in the displacements will go to infinity. Because when alpha goes to 0, we will know exactly what is the momentum, but we don't have any idea where is the particle. And kinetic energy, we have to do.
Just say for the kinetic energy, use like the fact that it's defined as the operator is squared. We need to calculate everything from the start.
What you suggest is saying, okay,
I don't
the
know
kinetic energy.
I just really don't
Let's
want
try.
to calculate
What
everything.
the hardest thing we learn during our physics bachelor degree is to try when we don't have a clue. So you say, let's have the momentum squared over 2m, like we did before. And you want to say, okay, so we know what is the momentum squared, so we can just write h bar squared alpha squared over 2m. This is your claim, right?
Maybe.
Why not? Let's think what is wrong about it. What is right about it? It just looks right, right? And it is correct. This is how we do it. But
how?
How? We know this is the definition of kinetic energy.
No, but if you say that the average value of the kinetic energy is non-zero, then how can the average of x be 0? Because you know it would move.
What is kinetic energy?
I mean, זה
moves.
זה מסתדר קצת עם אתנה, עם החוסר ודאות של ה...
The particle, okay.
כאילו עם אתנה בריבוע, זה גם הולך עם האלפא בריבוע, זה הולך עם האלפא בריבוע.
אבל זה החוסר, זה האי ודאות בתנה. פה זה האי ודאות באנרגיה.
לא משנה, תקשיב.
Think about it also in statistics, when you have a constant in the average, you have to take it out. So if t equals t squared over 2m, I'm going to take out the 2m from the average.
So what we have here is kinetic energy. Kinetic energy, what does it mean that the kinetic energy is 0? It means that the particle doesn't have any energy, it doesn't move at all. What we have when the average displacement is 0, it doesn't mean that the particle doesn't move. It means that it has the same probability to move to the right and to the left. It might be that the particle doesn't move, hence you have a displacement 0. But we do have a variance, meaning when you see this, you know that the particle starts from here, moves a little bit to the right, to the left, to the right, to the left, more to the right, and so on. It moves all the time. It has kinetic energy, it has movement.
Okay, now. And the momentum must be 0 because momentum has like a direction. And if it's non-zero, then it must be going in certain direction. Okay.
You should ask this Richard to be sure.
Okay, okay, but it makes
So it's correct?
sense.
Yeah. That's all.
Yes. less integrals to calculate.
I just opened a lot of place to mislead you. Okay. Great. Now we want to talk a little bit of the uncertainty principle. The uncertainty principle in general applies to any two operators. In general, usually we talk about it in this course in the sense of the uncertainty in X and the uncertainty in P. But it works for any two operators. And we will learn about it in the future. However, let's look about the uncertainty principle.
Any operators?
Any two operators.
With the connection would be no?
If the operators are connected, we're not going to have any uncertainty. If we look about delta x and delta x, we're not going to have any uncertainty. But there is a generalization of the uncertainty principle for any kind of two operators.
So it needs to be like in energy war, כאילו
Energy
בעולם
time.
האנרגיה יהיה כאילו...
זמן.
אוקיי.
Energy time is another combination of uncertainty principle. This is just like some background in intuition. It doesn't have to be momentum and displacement. So we know that for that, when we have delta x delta p, it will be larger or equal to h bar over 2, where delta x is defined to be the standard deviation minus x squared, and delta p, same for the momentum. In our case, delta x is equals 1 over square root of 2 alpha. From here, delta p equals to h bar alpha, and delta x, delta p equals to h bar over square root of 2, which is larger than h bar over 2. So the uncertainty principle works in our example. We can try it for any example. For any example, we will get that delta x, delta p will be larger or equal to h bar over 2. Here it's equals to h over square root of 2. Questions?
Does the uncertainty principle have like a certain scale that it should apply to? I mean, say that I know your momentum and your place in time, in space and time, and it's not, it's not satisfying this uncertainty principle.
Say it again. Use maybe a little bit more words. Maybe try to be a little bit clearer.
Okay, so we know that any system must satisfy this equation, right?
Any
Non-equation,
system must apply this equation: delta x, delta p, larger or equal to h
Yeah.
over 2.
But does it have a certain scale? For example, talking about electrons and stuff.
It talks about wave functions specifically.
Oh, okay.
And when we have a wave function and we derive the moments of x and p
Okay.
in this way, we're going to get this result. What you try to say is what I referred to before when I said we might have some general two operators and we're still going to have some kind of uncertainty principle. We will learn about it in the future. Here it's just like a simple case of the uncertainty principle,
Okay.
which is what we like to do as an introduction to this concept. ביי.
תודה רבה.